Good evening or good morning, wherever you are. So welcome to part 3 of chapter 5. So we are going to look at flow nets. But before we go into this chapter, let us firstly recall what we did. So we looked at how to determine K. We looked at we can have layers. If you have layered soil or strata, you can determine the horizontal permeability using this formula. And also you can determine the vertical permeability. How water moves vertically, how much at the speed at which it moves using this, the behavior, the permeability of how water moves through a soil vertically. You can use this formula. So we said that it's very important to determine permeability because we said that it helps and to determine to estimate and solve a problem involving piping. Seepage or pumping seepage or piping, okay, or heaving of soil. So it's important. So how do we? So before I go that side, I'm going to briefly talk about heaving. Okay, heaving. So if you have a pressure on the soil, if you are digging your foundation, and you dig your foundation, and this soil is water is stopped under here, but when you reduce on the effective stress of this soil, so we say to force water to pipe through this excavation, to pipe, what piping, to form holes and water start oozing through. Is that okay? So we say that if, for instance, if this soil, let us assume that the water table was just near this point here, at this point here, and this height of this layer, let us take it to be Z. Is that okay? And this material is saturated. Is that okay? This material is saturated. So the effective stress of this material, if this is the saturated unit weight, SAT. That's the saturated unit weight. So the material, the factor of safety against piping, factor of safety against piping will be F. That's called factor of safety against heaving will be equal to effective stress. That effective stress will be Z into unit saturated unit weight minus the unit weight of water divided by the lifting force. So the lifting force will be the head of water, will be the hydraulic head, H, times the unit weight of water. Then the unit weight of water, W. Is that okay? So if the factor of safety is high, now this head here is determined. It can be the hydraulic stat or the water, the approximate water pressure at which the head of water which will push the water through this material. Is that okay? The head, the water, is that okay? So this will be the factor of safety, S. Okay. Now for instance, you may want to design, you have found that this water when it rains, okay, it will cause a flood head of H. It's in the swamp. So in doing an rainy season, the water is just at the surface. So we need to determine the amount of fill to put on this ground so that this piping doesn't occur, so that the water is not pushed out due to the increase in water in the ground due to head H. And this head may be the rainfall which will be received, which will cause water to flow through this foundation. So okay, this will be the head. So how do you design that? So let us assume, I'm going to assume this is the existing surface when the water table is just near the surface, is saturated, material is saturated. So we are going to assume that we are going to add another material X of depth X. We are going to assume that the properties of this material is the same properties of this other material down here. Is that okay? Of height X. Is that okay? Of height X. This is 8X. Then this is a known material. Let us talk depth to be H, the existing material. Is that okay? So therefore, all these two, they form up Z. This is Z, total Z. So that you have Z is equal to X plus H. Now, if you want to determine the X, you already have the thickness of H, and we have that now if we assume that the properties of this material are the same properties of this other material. So you want to determine the X, how much should you add so that you prevent uplifting or piping? Which material should you need to add? So to get the material, depending on how much water the pressure head which is going to come in, so the factor of, you are going to assume the factor of safety of 3. Factor of safety, let us take our factor of safety to be equal to, factor of safety against piping to be equal to 3. Is that okay? To be equal to 3. Therefore, now for our part is to determine Z. Is that okay? So our Z, which will be H, this is known, the thickness of that layer in which the saturated layer is known, H. Now I want to determine this H. Now so it will be equal to factor of safety against piping. It will be equal to, so it will be equal to, now for the effective stress, now for the effective will be the pressure, which will be 3. We go back to this equation. 3 times factor of safety, which will be, this will be 3, which is factor of safety, times the uplift force, which will be H. Maybe this will be the rainfall which has rained, which will increase the pressure head of this. Is that okay? Is equal to, is that okay? Or it may be equivalent to the construction which you are going to do, which will cause a pressure movement of water which is equal to this. You can determine this height. Now for the pressure, which will be there, times 3 times H times the, is that okay? Should be equal to Z into saturated unit weight minus unit weight of water, W. Is that okay? So this is 3. This is a factor of safety. Our factor of safety is 3. We have chosen 3. Is that okay? So we have 3 here times uplift force should be equal to, for equilibrium. Just a point of for equilibrium, this should be equal to Z times Z, which will be equal to the effective stress. Is that okay? So with that, if you at this point, then you, with the unit weight known, saturated unit weight known, and unit weight of water known, H is known, which will be maybe the flood, the height of the flood you have received. Is okay, or you will receive in the amount of rainfall received in terms of millimeters or millimeters. Then you have determined, or it may be a pressure. This uplift force may be as a result of constructing, maybe as a result of imposing a stress into a water body, underneath water body, which comes from a building which has been constructed here, and this is coming from a pressure increase. Is that okay? A pressure increase will cause water to flow out. Is that okay? There may be an pressure increase, should be equal to Z. Now, which is Z? Now, for this Z is a function of X plus H. This H is the thickness of air which is known. Is that okay? So from there you can determine the Z amount of fuel to put so that you adjust a point of equilibrium. Is that okay? Now for this one, X will be the amount of fuel to put here to prevent heaving or piping. So okay, to prevent heaving or piping. So that's one of saying, because one of the importance of determining permeability or doing this work is be able to predict is to be able to predict or to solve problems involving pumping, seepage, or some people call it piping, seepage, water from construction, excavation. Is that okay? So able to solve such problems. So able to determine how much should I excavate to prevent such conditions of piping. Is it okay? To prevent such conditions of piping, or what the amount of backfill should I need to put on a place where like a piping will occur to prevent, due to the construction of a structure, will impose an effective stress. This would be a pressure, an uplift pressure. Is that okay? An uplift pressure. Okay, so let's look at our flow lines. We have recouped, or we have been recapping. We've been recapping of what we discussed previously. So I look at flow nets. So for flow nets are normally is the construction of flow lines under a dam. Is that okay? To predict how much water or how much water flow through a dam, a dam retaining structure. And also you can be able to determine the flow or the uplift force which may occur due to the flow. So the flow of water through a soil can be represented graphically by a flow net, a form of curvilinear net made up of a set of flow lines intersected by a set of equipotential, a line of points of equal potentials, or equal pressures. Is that okay? Equal potential lines. The path which water particles follow in the course of seepage are known as flow lines, or university flow lines, which water flows from points of height, which is known to points of low head, and makes smooth curves which change directions. Hence, we can draw a series of smooth curves representing path of flow by moving water particles. Then the equipotential lines, as water moves along the flow line, it experiences a series of loss of head, okay, loss of pressure. If we can obtain the head causing flow at points, at points along a flow line, then by joining up points of equal potential or equal head, is that okay, or equal pressures, we obtain a second set of lines known as equal potential lines. So I'm going to take an example. Let us assume this is the flow line, and this is a place in this point here and this point they have equal potential. This is a point, and the distance between these equal potential lines, or along this line, is have equal potential. This point and this point have this equipotential line. Is that okay? Or equal potential. Is that okay? Is that clear? So the flow, how do you calculate places of equal potential in this area? So the places of equal potential. Now, for instance, if you have number, of course, we shall look at find out to find the number of equal potential you count. So for instance, here this is 1, 2. Now for these lines here, this is the first equal potential line. So, but to count the places where I have equal potential, be 1, 2, 3, 4, 5, 6, 7, 8. So that is the bound. One equal potential is the area bounded by equal potential lines and the flow lines. Is that okay? So B will be the NF will be 8, but we shall see what NF is. But before you go there, the issue is to determine flow. Is that okay? You know that, remember, the water is flowing perpendicular to the face. This is water is flowing perpendicular. Now this into the paper. Let us take a meter width. Is that okay? A meter width. Is that okay? But you know that flow is equal to K. K times the pressure difference times area. So that's the area is B times 1 per meter width of the what? Per meter width of this dam. Is that okay? Into per meter width going this other side. If we do a 3D per meter width, it assumes that in this section here we have a meter. This is a meter. So per meter, this is B. Is that okay? So that if for area, remember at flow 2 are very same. That 2 is equal to V times A. What we have seen, is that okay? V times A. So what is V? V is equal to K times I. Is that okay? Now for I, what is it is so is equal to H over L. Is that okay? I is equal to H over L. I, this one here, is H over L. Is that okay? So our H is the potential, the change in potential at this point. Is that okay? Full at this point in this area here. Is that our area? Is that okay? In this area, we're talking about this area. Now for this area, but I'm talking about the other side. Remember, now for the area, this is the equal potential of which is equal to change in H. The change in H is the pressure. Now for this, the pressure difference from this one, from this point, from this area to this enough will be H from this point to this point here. Sorry. Is that okay? That will be a change in H. Is that okay? That will be now for change in H divided by L1. L1 is the length from here up to here, the length at which the water moves. Also, water covers the length from this point to this point. Is that okay? And the pressure difference, which is changing H from here up to here, is changing what? Changing H1. Let's consider this will be our H1. From here up to here, there's a change in pressure. Remember, this is somehow inclining. Okay, there's a change in pressure, which pushes the water, which pushes this water to fall to this point. Now, for the water to move through a distance of L1. Is that okay? Now for this one, the change in H1 over L will give us our I. Is that okay? Where the L is the length between two equal potential. Two equal potential lines. Is that okay? Is that clear? So that being understood, so now what has the times B times 1. Remember, we have per unit per meter. Therefore 1 times B, this is B, times 1 to give us an area. Remember, there is this distance from, if we swap down here, this is B, this is 1. Now for water is flowing through this area, it's perpendicular to this area. Is that okay? Now remember, per meter, length of the what? Of the dam. Is that okay? So B at is times what? Times 1. B1 times 1 gives you an area. That gives you Q. Remember, Q is equal to V times A. Where V is changing H1 divided by L, where A is B times 1. Now for the flow here, using the continuity method, remember Q1 is equal to Q2 is equal to Q3. That's why this one here is equal to Q2 is equal to Q3 in this other line. The flow is uniform. Is that okay? So when you equate them, we shall find that B1 for this to be equal to mean that B1 and L1 to be the same. Therefore, should have square. Is that okay? B times L has to be the same for all these fronts for the flow to be uniform. Is that okay? For the flow to be uniform, we assume that all that will be uniform. So that this over this should be equal to 1. It's equal to enough. It should be enough for giving us squares. The flow line, the flowness should be equal to a square. Okay, so this flow is to be the uniform, as I've said here. Now the change Q1 is equal to Q2, all this to be the same. Is that okay? The flow to be the same. So in the end, find that in order to construct your flow line, now for these dimensions, L times B should be square. That this one should be equal to this. This one should be equal to this. Therefore, this should be equal to that approximately. And where they meet, where equal potential lines. This is an equal potential line. Means a flow line should make sure that you get 90. This would be this is a flow line. Is that okay? So this is an equal potential line. So equal potential line meeting a flow line here should have a 90. Is that okay? So you do small and then you do it by free hand. Is that okay? Using a free hand. So how do we calculate this? So remember, we say that flow Q is equal to K times B over A. This is L. Is that okay? B, we said B and L should be equal to 1. Therefore, this gives us equal to 1. Therefore, our Q is equal to K times DH. Is that okay? But we find that change in H is equal to H over ND, where ND, this is the number of equal potential drops. It is changing. Is that okay? By equal potential, we divide this H into the number of equal potential drops so that we can get the small change in Okay. Then n chu is equal to chu over n chu is equal to chu over n nf, where nf is the number of flow nets. That will give you the flow. Therefore, the flow per flow line is equal to, remember we said it is equal to chu times what? Therefore, per flow, if you want to get the total chu divided by the number of flow lines to give you the total chu. Therefore, the total chu will give you the number of flow lines. This one, the number of flow lines, we give it to summation of what? To summation of the flow. You divide. So now for using this equation, now for this equating it to this times k, now for we can make chu the subject. Equating these two can make the chu the subject. Is that okay? Now for chu is equal to kh, where h is the head, this head here. Okay, and K is the permeability of the material. That's why it's important to determine K, the permeability between the impermeable layer and where the dam is constructed. If the dam is not constructed with a permeable layer, for this material it may be clay. It may be clay. Is that okay? Now for the amount is the rate at which water flows, the properties of the material, which the ability for our water to pass through it. That constant, that constant, the K. Then the NF and ND is what now we need to determine. So how to determine NF and ND? You can determine NF by constructing the flow net. Okay, by constructing the flow net. Is that okay? So how do you determine how to construct the flow net? The first step is to identify the first flow lines. The first flow lines are either the bottom of the dam or the impermeable surface. These are the flow lines. Now remember the flow lines should be tend to be parallel. The last flow lines will be principal to the last flow line. Is that okay? And also around the sheet. Remember water will flow along here. It is known. If this is a sheet pile, this will be a flow line. Because water will come and stick and flow along it. Is that okay? That will be a flow line. So this will be a flow line. And so down here also we have water flowing down. Is that okay? These are the boundaries. Is that okay? So the next one is to find, after identify these boundaries, the boundary conditions. This is an equal potential line. Remember here at this point here, the pressure is the same. Along here, the pressure is the what? If this is water, the pressure here is the same pressure here, the same pressure here. What pressure here, the same pressure here. If you have here water here, for instance here, the pressure here is now for this is equal potential. This line is an equal potential. This line here is an equal potential. Is that okay? And also this line here is an equal potential. The potential is the same. The pressure is the same. The energy, the pressure is the what? Is the same along this line. Now this is an equal potential line. Is that okay? So the next step is to do the first flow line. The flow line. Therefore, I said if this is equal, now if you are going to do the first flow line, the difference is you take this to be we have the flow line along here. Is that okay? So we have a flow line along here. We already identified these flow lines, and also have a flow line here. We have a flow line here. They're coming like this, and the flow line here. Next one is to draw the next first flow line apart from the boundaries. The boundary. Therefore, remember this is an equal potential. So water will flow from this point here, flowing in such a curve. Because now we need to bypass this. Is that okay? Because we have the one which is flowing along this, going out. Is that okay? But also we have another one which should come and bypass this. Is that okay? So we should have another flow line here. So after identifying this, I draw a first flow line and hence establish the first flow channel. And now the water will be coming, flowing out like this. Between this flow line and this flow line, we have a flow channel. Is that okay? So the next one, now to divide this to approximate with the points of equal what? Equal potential. Okay. So now for this one here, you draw this. So this length here is equal to this length here. So you come and divide, and then after divide. Now for this one here should be this. The next division here should be equal to this using a protractor, and at 90. The first point here should be 90. Go to the bigger one. This point here, you see, this should be vertical. It should be like a cross line. Now use a protractor to approximate draw a 90, but then you curve them so that this length here is the same length here. Is that okay? The same length here. It's the same length at this point. Is that okay? The same length at this point. So for this case was our first one. Then you come and draw this. Is that okay? So after drawing the floor, after doing this equal potential lines, but mind you, this is and this is a flow line. So therefore, you can come and join this to come to produce this equal equal potential. Remember, this is a flow line. For a flow from a flow line, you can draw an equal potential line. Meeting this also to 9. Remember, they have to the equal potential meet with the flow line at 90. Is that okay? Remember, you have a flow line here, so this line should be able to project them as you draw. Make that this when they meet the surface of the flow. After that, divide the first flow line into squares. Divide them into squares, equal squares. Is that okay? At least the first at first. The use of compasses is necessary to check that in each figure B is equal to L. 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 Is that okay? But after some practice, this sketching will proceed, can be done by using an eye. Is that okay? Then project a potential line beyond the flow line. This will be the case here. Step C. You project them below the flow line. Then after that, after projecting it, with the compass, determine the position of the next flow line. With the compass, remember I said this is why we use the compass here. This you should need to approximate. Is that okay? To approximate that this one here should be able to be equal to this one here. Is that okay? So you approximate. That's why you are using a compass. Indicate the indication of which gives an indication of the size of a square in the next flow channel. So you can you approximate a square here. Okay, approximate a square. Then so that you can come up with this other line, so that when you join this one, when you bring them down, you have a square. This length is equal to approximate. Approximate means that it doesn't have to be at the difference. If you divide by this, the difference should be about 1.15. The difference. So this B divided by L should be at least 1.15. An approximate square. Is that okay? That's why it is an approximate. Is that okay? Then project the equal potential and repeat the procedure until the flow net is complete. You proceed. So it is an approximate method to draw a flow net. So now let us look at an example. So I finished concerning the flow net as an example now. So that from figure F, that is for figure 2.9F, this figure here, determine the loss through seepage under the. Now for this water, remember there is a dam here. This dam is made to retain water, but the water will be moving under the down here to go downstream. Is that okay? There will be loss. Remember, you are retaining water made for agriculture, but there may be loss through seepage. Is that okay? Now, one time, how much water is lost through seepage? The length of the dam, perpendicular to the plane, is enough. The length of the dam, this length here, this dimension of the dam, this. When you continue with this dimension, perpendicular to the floor. Perpendicular to the floor is the floor that is what? 30 meters. Now for determining Q, remember the Q, we said that Q, this is per meter. Per meter, width or length of the dam. Per meter, this is per meter. This is Q, per meter length of the dam. Remember we said that our B is times 1. Remember that B times 1, that is per meter width or per meter length of the what? Of the dam. Is that clear? So if you can come here. So now timing. Okay. So the first thing is to time our formula is that Q, which per meter length of the dam, is equal to KH into NF over the NF is the where NF we said NF is the number of flow lines and ND is the number of equal potential difference. How do you number of flow lines? It's an approximation. So flow lines will be can be 1, 2, 1, 2, 3. But remember, this is an equal line, flow line, this is an equal line. So we can take this about 4 or 3.5 or 3.3. 1, 2, 3. It's an approximation. So I'll take it 3. Okay, I'll take it 3, or you can take it for about 4. Between 3 and 4. Okay? That be the equal potential line. Then the ND is the number of equal potentials. This is 1, 2, 3, 4, 5, 6, 7, 8, 9. The divisions. Remember, this area is an equal potential. Is that okay? This square. Be 1, 2, 3, 4, 5, 6, 7, 8, 9. Is that okay? 1, 2, 3, you can 9. So we have 9. So we have our end is equal to 9. Is that okay? Now for the pressure, we see that the level of water above the dam is 4 meters, upstream, the downstream 2 meters. Now for the H, the pressure difference, the H, the one which is causing seepage, is equal to 10 minus 2, which gives us 8. So substituting this formula, we have your K, we have our 8, we have N over D, we can determine the flow per meter through the dam. Then to get the total seepage under the whole dam, we give you 300. Because I said the total length of the dam 300, because it was per meter. 300 times the area is 60 days. Remember it's per second. Now for you to return this second, then you have to multiply times what? Remember it's cube. Now for times time. Times time. So to get times. Now our time is what? So you need to convert a year into seconds. So a year is 365 days. Each day has 24 hours, and each hour has 60 minutes, and each minute has 60 seconds. Is that okay? Time